So are we good to go?
Just a second. Yes, we're good to go. So hello, everyone. I'll do this in English. Welcome to another meetup. Sorry for the confusion. We confused the links. We published the links for the previous session. So I hope that if you want to be here, then you are here. Otherwise, probably not. We are recording this session anyway, so it's going to be available later for you to watch. I'm not going to say too much. I'm going to welcome Zoran Barak. He's going to talk about Azure SQL, specifically different service tiers, comparison between Hyperscale and other tiers in Azure SQL databases. And I have a problem with my camera, so you can't see me. Lots of problems today, but I'm going to shut up and let Zoran do the rest. It's all yours.
Yeah, excellent. Thanks for introduction. And hi all, welcome to this meetup session. And I want to say thank you for the organizers for organizing this. I know it's time consuming, and I'm as well the SQL group, Oakland SQL group organizer. I know how difficult that is with managing all that with the ongoing work you have. So we're gonna talk about traditional Azure SQL architecture, and we're going to compare with the hyperscale Azure SQL architecture on Azure cloud offerings. I want to apologize if I start talking a bit faster at some point, because I need to cover all that in 60 plus minutes. And it's quite a big topic. And as well, my voice is a bit rough. I was sick like the whole week, so I'm still coughing, but I'm going to do my best to be as much as possible understandable. So this is me. I'm a principal data architect in New Zealand, Auckland. This is my details. I'm working with the data for over 15 years now, and I'm also MCT certified Microsoft trainer, and organizing Auckland SQL user group and doing those sessions, events across the globe. And this is my details. Like if we do not cover everything on this session in the 60 minutes, or so, you can contact me anytime, and I'm going to try to help you as much as I can. Okay, I'm going to put this laser pointer just in case if I need to show something on slide. So this is my recent book. I wrote this book with my colleague from Microsoft, Daniel. It's published in March. It's about the hyperscale in general. And if anybody's interested, I just put the slide here. So this is agenda for today. We're going to talk about the Azure SQL PaaS platform as a service offerings. We're going to cover 4 concepts, how the Azure actually give you those offerings available, those deployments available. We're going to talk about deployment models, purchasing models, service tiers, and availability models in the back. Those availability models actually dictates your architecture. And we're going to talk about the traditional Azure SQL architecture, and then is the main topic for us today is going to be hyperscale architecture, and going deeply in decoupling the compute, storage, and log service, and how some of those existing features are used to get the architecture, hyperscale architecture in Azure we have today. As well, we're going to see SQL database hyperscale at work, how that's actually working, and I'm going to give you some testing results I did earlier, so you can actually compare the traditional one and the hyperscale one. So this is the first part. This is the traditional Azure SQL platform as a service offerings. Just to better understand, hyperscale is just a service tier of a single Azure SQL database deployment. It's not like any other different area of Azure SQL PaaS. It's just a part of an existing one, but it's just how it behaves and work in the back is different. So here we're going to cover the traditional one and explain what is actually how the architecture there actually look like, and redundancy as well, and everything which is following. So this is what we have on the Azure Cloud SQL Platform as a Service offering. So we have a deployment models, and there we have Azure SQL Database, Azure SQL Managed Instance. On Azure SQL Database, we have a single and elastic pool. On the managed instance, we have a single instance and instance pool. We're going to explain those ones, and we're going to scratch the surface. We're not going to go too deep, because what we are looking for here is the Azure SQL single database, which actually can go and offering us hyperscale service tier. But we're going to explain the architecture behind all of them, traditional one, so to speaking. Then you have a purchasing models and service tier. You have a purchasing model is the DTU purchasing model, a vCore purchasing model. Behind those purchasing models, you have a different service tier. Those different service tier leveraging different availability models. So you have here DTU purchasing model, basic and standard is leveraging the standard. General purpose vCore leveraging the standard as well. But premium DTU and the business critical vCore, they're leveraging the premium. Hyperscale, which is belonging to the Azure SQL single database, leveraging the Hyperscale multi-tier architecture. It's completely different. And you're going to see in a few next examples. But let's start first with the traditional one. With all deployments, actually, including Hyperscale, because obviously we have a single database here, which offering us Hyperscale as a service tier. But let's mention and understand what other offerings we have there so we can actually compare them. So the managed instance, as we already mentioned, we have a single instance. This is fully managed service, same as the Azure SQL database. It's the only difference is it's kind of like when you look on the interface, it behaves like on dedicated or VM infrastructure as a service kind of deployment. You have everything as what you would have on your dedicated machine. And it's kind of easy migration. It's a lift and shift kind of way of migration. It supports all on-prem instance database level capabilities. You have Azure hybrid benefits as well. It's 94.9% availability guarantee. So built-in backups, patching, recovery, everything is fully managed. So for instance, pool, basically, it's add-on to this. You can go with the less core on instance pool. It's for a single one, it's a 4 core, I think is the minimum. Here you can go 2 core per instance. It's used mostly when you want to have those smaller machines in the one pool. You can't deploy this still via portal, so you need to use the Azure CLI, and or you can use the PowerShell or something like that to use as your deployment. But once it's deployed, you can actually access via portal. So you have a databases, Azure SQL databases site. That's a single database and elastic pool or pool databases there. Single database is offering you hyperscale service tier. And as well, provisioned, and you have a serverless since the March this year, just recent, like 2-3 months. It's available serverless as well for hyperscale. And you have a serverless compute tier for a general purpose as well. It's a fully managed service. You can go from 4 nines, 4 nines, and 5 availability guaranteed, depending on which deployment options and service tier in the back you use, because as I already mentioned, those service tier actually leveraging different availability models, and those availability models actually guarantee you that availability and how that architecture in the back is going to look like. As well as the previous one, you have a built-in backups, patching, recovery, and everything. Latest stable database engine version. And that's really important to remember, because when you do migration for the current dedicated one or infrastructure service, you need to understand which version you currently have, because on PaaS, platform as a service deployment, you're not going to be able to choose much. Is what you're going to get is the latest stable database engine version. Elastic pool is kind of option for you to put those single database within pool and cut the cost with that. And it's a price optimized kind of shared reasons kind of way, because you can have, like in my case, New Zealand databases. I put like for a cost of 10 databases, one elastic pool, I put 20 databases, 10 of them in New Zealand, 10 of them in USA. They have a different peaks time, so I can work with that to actually, for a cost of 10, running 20 databases. But you need to plan your workload, understand your workload, and that's feasible. That's actually a lot in use. You can limit the resources per database, and it's fully managed service. So let's move on. We just scratched the surface. Now we're going to talk about those availability models. We talked about deployment options. We talked about the service tier and the purchasing models. Now is availability models. So as we've already mentioned, those availability models, you have 2. You have a standard and premium. None of those is actually hyperscale. That's going to be the third one, so to speaking. But the standard availability model, it's actually 3 of service tier in 2 different purchasing model, DTU standard basic and vCore general purpose is leveraging this one. So it's work in a way that is separate your holding your LDF, MDF files to the shared storage. It's kind of kind of separate the compute from your actual files and actually your data. It's a bit slower than the premium one, and I'm going to show in examples why. 5 to 10 milliseconds latency on average. I'm not going to separate writes and reads. I'm just talking about the average kind of thing. And it's kind of like target budget-oriented business applications, and you can accept the performance is not the top tier. Premium availability model, that's DTU premium. And you have on vCore purchasing model, you have business critical. They're leveraging the premium availability model. This is attached SSD directly to your nodes. And I'm going to show you, and I don't need to remember all this. It's just like scratching the surface before we move on. I'm going to show you all that in architecture, for a traditional architecture, how that look like. It's actually working same as the HA would you have in your dedicated machine. So it's availability kind of the full Windows failover cluster kind of way. Although it's not the same because there is a fabric, Azure Fabrics in the back, which dictates when the failover is going to happen on basis of the healthy status of your node. But the accomplishment, like the final result, is exactly the same, and it's a fully synced. So they basically behave as the same as what you have in your HA availability. This is for a mission critical application with high performance. It's 1 to 2 milliseconds latency, so it's quite fast because of the attached SSD directly. So any of those deployments you choose, you're gonna have one way some redundancy. Like you're always gonna have a local redundancy. So if your primary is down, even if you don't have a readable secondary or a HA secondary in kind of way, you're still gonna have a node with a spare capacity which is gonna take over your role. But that's gonna be data center kind of related. So it's gonna stay there. There is no regional. If there is a regional outage, if data center is down, even if you have multiple data centers in that region, if your data center is down, you're gonna lose the accessibility. But you're gonna have your backups on geo-redundant storage, so you can restore somewhere else always. Zone redundant availability, it's basically the same region, but in different zones in that region. So you need to deploy your database to the region which actually support multi zones. You need to choose a particular region location. That's still not DR. If region is down, this is down, but your backups, again, they are geo-redundant. Geo-redundant availability, you can use different ways how to accomplish that. You can do it via code. You can create DR using some asynchronous application, or you can do the failover groups and actually accomplish that. This is how the basic standard and general purpose service still look like, because they're using the standard availability model. So the standard availability model is actually offering you what you can see. You have a Azure Premium Storage that's locally redundant storage for the data and the log files. So if this is gone, obviously it's attached to the one DC, and it's probably the one rack. Those actually is not the one rack, because all of those deployments feature actually forcing the file domain and the update domain concept, which means that when you deploy this, they guarantee you that those nodes is not going to be in the same rack. But still, you can see the backup is on geo-redundant storage. So if this is down, you still can restore your backup somewhere else, but it's not going to be accessible if this data center is down. So it separates compute layer from a data files and the LDF files. It's a bit slower, 5 to 10 milliseconds, but the SSD and all the model database, plan cache, buffer pool is all staying SSD attached to the node. But if node is gone, you have a node with spare capacity. It's already failed. You don't need to do anything to get this. You're getting this with just push of the button in deployment. And automatic failover is based on Azure Service Fabric. So it's basically when Service Fabric see that something is wrong here with your node, it's going to fail over for you. So you saw in this slide, we mentioned basic and standard. This is DTU. Now we're going to the general purpose vCore, which we had in the previous slide. We have it here because this service tier have option of zone redundancy. So this is a zone redundant availability. It's still standard one, but you can see that those nodes with spare capacity now living in the different zones, still in the same region, but a different zone. So if the data center holding your first zone in the zone 1, holding your primary node, primary replica. If it's down, you have a secondary immediately up, and it's taking role. You don't need to do anything. Basically, everything is going to be redirected. There is some latency between those, and it's going to be some cost on a general purpose vCore. But you can see now in the previous slide, this was local redundant. Now it's zone redundant for your Azure, for the data and the log files. It's Azure Premium Storage still, but it's zone redundant. That there is a latency because of that in between them. And the backups again, geo-redundant as always. So this is like zone redundancy, still regional, but you have option to, in case if your data center is down, to switch to another one. This is the premium availability. So we talked about the standard, we talked about the standard availability, DTU standard and basic, and the vCore general purpose. But this is a premium availability model. So you have a DTU premium and vCore business critical there. They leveraging the premium availability model. So in this case, you can see this is more like your always on HA. So you have 4 nodes. Whenever you deploy, you don't need to do anything. You just deploy your database. You're gonna have this. You can, or you, I mean, it's not by the default, but you can have a read scale out as well. So one of those is gonna be your readable secondary. So if you have an application intent read only, it's gonna go directly there. So this is how it look. It's look like exactly what you have gonna have in if you put the 4 VMs in a infrastructure as a service VM or a dedicated machine somewhere else, and create your Windows payload cluster and create your HA there. Is gonna look like always on availability. Is gonna look like that. Your data file, log files, they're directly attached from SSD to the replica. Only TempDB is not shared there, but they're fully synced here. It's a fully synced. And if one is gone, second just taking over the role. Again, automatic is failover is based on service fabric, same as the previous example. If there is issue with the primary, it's just going to fail over in the first secondary available. So all this you can put in a zone redundancy as well. So for a zone redundancy, you're going to have the same thing, except you're going to have a different zones for your VMs. So VMs, sort of speaking, nodes, replicas, whatever you're going to call them. But they're going to be in a different zone. So one is going to be readable secondary, okay, but when failover is happening, it's going to happen in some different zone. So this way you kind of like protected from a local outage of that particular data center or that particular rack. You're going to failover directly to some other zone, which is working properly. And it's because this is a fully synced, as you can read, it might increase the commit time and performance for your OLTP workload, because this is fully synced. You have a caps on the log throughput, which Microsoft can guarantee you. If you write that much data, we're going to be able to sync it in between. So we scratched traditional one. Now we're going to go to the matter of this session. This is the hyperscale now. So hyperscale architecture. Basically, what it's doing, it's as we said at the beginning, this is the single Azure SQL database, and just the service tier is the hyperscale, and that service tier hyperscale can be now, since the March, can be the serverless or provision since already a few years. So we're gonna talk about the decoupling the compute storage and log service, storage and log service, sorry. And how that actually work on a hyperscale and what we get with that. Because behind this, you have that horizontal vertical scalability, almost limitless horizontally, which is really hard to accomplish with the traditional one. I explain why. And you have we're going to talk about the hyperscale architecture foundation, which means like what was used to actually accomplish all this, which were existing way before the hyperscale, as accelerated database recovery, page versioning, buffer pool extension, and so on. And we're going to talk about some results between resource limits, traditional versus hyperscale architecture. This is going to be for this part. Later on in the final slides, you're going to see some performance comparison. So this is our hyperscale service tier availability. So you might see on the screen there is a log service completely separated, compute node completely separated, page service completely separated, as Azure Standard Storage as a holding our data and the LDF files. It's like 4-tier kind of concept there. It's going up to 100 terabyte size in database. So just to put in perspective, for an Azure SQL database, you can go up to 4. For an MI instance, if you go general purpose, you can go up to 16. For a business critical, you can go up to 5.5. I'm not sure if something changed recently, that those data and those numbers changing a lot. So nothing which I'm saying now about the numbers is written in stone. Just bear in mind that Microsoft is adding and improving this architecture literally daily. So they're adding, like when we started writing a book half a year ago, and when we finished, the serverless just become available. So we didn't have that in our book because we didn't even have that available to testing. But we finished the book in March. They published that in March. So basically, that's one example. And you're going to see a few examples through the slides and explain that. So what we have here as a characteristic is like what 100 terabyte, really important, fast backup and restore. I'm going to explain how fast and when is fast, when is not. Multiple replicas, you can go up to 4 read scale out, but what you can do is, I mean, it's HA and read scale out. They can take both roles. But what you can have is the named replicas and geo replicas and so on. I'm going to show that all across. And the hyperscale is obviously, as we already mentioned, multi-tier architecture is actually relying on these 2 tiers here mostly. Those are the caching layers, which you want to actually to get your data off. You don't want to read from Azure storage because obviously it's a slow way to access data and read data from. And one example here we have a note in April 2022 is you couldn't, before that, you couldn't migrate back to any other deployment. So once you go hyperscale, you couldn't go back. Now that's available. You can go hyperscale, test it, and do the rollback to the general purpose if you want, traditional architecture. But bear in mind, if it's a native hyperscale, so if you deploy the database as a hyperscale, you can't migrate back to the traditional one. So we're not going to go too deep in this. This is the basically foundation, what was used to actually get what you're getting now with the hyperscale. It's a buffer pool extension, exists since 2014. It's nothing else that using the attached SSD to your machine and extending your buffer pool and the memory so they can be used for mostly used pages. And it's the same purpose on a hyperscale as well. And the only difference is that the resilient buffer pool extension is on a hyperscale. This is the old one. Resilient buffer pool extension is the recoverable cache after failure. And the size of it actually depends, and it's attached to your cores. When you're deploying the hyperscale, you're going to say, okay, I want 2 cores, I want 8 cores, I want how many cores you want. With the cores, memory is going up. Hyperscale resilient buffer pool extension cache is going with that. So if you have, for example, I'm going to give you an example, 2 cores, hyperscale database deployment with around 5 something gigs per core, that's going to be a little bit more than 10 gigs of memory with the 2 cores. You will have 3 times that. So around a little bit about 30 gigs of resilient buffer pool extension cache on your compute node. That's really important to remember because there is 2 resilient buffer pools. You're going to have them on a compute node. You're going to have on page server. One is covering cache. One is not covering cache. The second thing which existing again for some time is the row versioning. So we all know when row versioning is enabled and used, it's basically creating a table on the TempDB and storing those historical values. And by default is off for a dedicated deployments. For instances, you deploy an infrastructure as a service or some dedicated machine. But for Azure SQL platform as a service deployments, it's on. So you're going to have for your primary, you're going to have a read commit snapshot. For a secondary and readable secondary, you're going to have a snapshot. The main difference is that just the scope of consistency. So read commit snapshot is the statement level consistency. So you might have non-repeatable reads if you're running in the same during the same transaction. And the same time, it's transaction consistencies for a snapshot, so you're not going to have those issues with that. What else we can say here? Yeah, those. What would be the main difference? What we have now and what we had before, and why we mentioned this row versioning is that what hyperscale architecture. You know that those temp tables holding your historical values for a version store, so-called. Were in a local TempDB. Now, that's available just for that particular instance. Now, what Microsoft did with the Hyperscale, it forced Hyperscale architecture to extend that shared disk ability in such way that force compute layer to share that on a shared storage tier with other page servers as well at the same time, and creating the persistent version store. So in case of failure, you can utilize the next step, which is going to be ADR and recovery much faster, avoiding using the undo during your recovery. That's how the ADR actually works really fast. You know that before, when we had a rollback, that was taking time. Now this, with all options we have in place, this is really fast. So let's go.
I have a question, Zoran.
Sure. Yeah.
Raw versioning and ADR both are available by default for all service tiers of Azure SQL database.
Yes. Yes.
So I maybe I missed it, but what is there a difference for Hyperscale compared to other service tiers?
Yes, the Hyperscale, this raw versioning if you're using raw versioning in dedicated machine or anywhere else, you're gonna have a TempDB just locally available.
Yeah.
It's gonna be held in a local temp. It's in the TempDB basically as a local table. What is doing Hyperscale is pushing that to the shared storage tier.
Oh, okay.
So it's going to be available, not just the compute have that access. It's going to be available for a page servers. Depending on the size of your database, you might have 10 page server in the back. They're all going to see what is your historical value of your data. So if something happened and need to recover, they don't need to do the undo version, undo process from ADR. It's just can pick up those rows and just apply them.
Okay, thanks.
It's going to skip, like, when we had that areas recovery model, which you need to do I believe the order was analyze, redo and undo phases.
Yeah.
Now that undo is going to be skipped, and I mean that's how it works generally everywhere. It's not just here, but now you're going to have those tables with the historical values available to every single page server. And you're going to see later on when we talk about page server, every page server is going to hold just a set of data, not the whole database, just from 128 to 1 terabytes. I'm going to explain why is that difference. If you go with the native one, it's always going to be 128 gigs.
Okay, thanks.
Yeah, no worries. So we're going to go there when we go to the portion where how this actually works. And I think after this slide, basically we are going there and we're going to explain primary compute node, secondary compute node, replicas, log service, page server, and Azure Standard Storage. So this is the resource wise. Now I'm not, like, just to be clear, I'm not cheating for any of those two. I like traditional one because it's also always depends on your workload and depends what you have and what you need. You're not gonna force Hyperscale just because it's new available architecture. You're gonna go to Hyperscale if you need Hyperscale. I just want to give you some limitations. This is a resource wise. Then we're gonna talk about the performance and we're gonna talk how that actually works in the back. So resource wise, we can talk about the max storage, CPU, memory, latency, log throughput, log size, read, scale out, and backup and restore. So for a max storage size, all those numbers are pulled like maybe 2 months ago. So they're changing. As I said, it's not written in stone. Don't take them for granted because maybe when session is done in 2 weeks, it's going to be different. So for a Azure SQL database is 4 terabytes. For a Azure SQL MI business critical service, it is 5.5, and that was changed from 4 kind of recently. Then for a MI general purpose is 16. So why would be that big difference? Look, we can debate that, but I would say because the business critical is fully synced, you need to take care of those commits in the back. They need to be synced. You can't, with the general purpose, if even there is a delay, you don't have a secondary you need to read from because it's not available on a business critical. Yes, if you enable rescale out, you want the data to be synced quite quickly. So to accomplish the SLA, they need to do and limit and putting the cap on the log throughput, which we're going to explain here. So you have a hyperscale architecture, 100 terabytes. That's the size. Basically, if in theory, it's unlimitless, but I believe that Microsoft needed to put some kind of cap and say up to 100 tera. Because you can, those page server is going to be added by itself. It can add like thousands. CPU, up to 128 cores. This as well is changing a lot. So during the writing the book, this on the hyperscale option, which family were available there, they changed that in the middle of the, like, I think it's November, December, they added a few series. So this is the standard series Gen 5. It's up to 80 cores. Premium series up to 128. There is another one, premium series, but this is a memory optimized. It's going up to 830 gigs of memory, but it's just 80 cores. So again, you need to understand your workload, what is sufficient for you. That means that just a petacore, they give you more memory. That ratio is different than ratio what you have here. So for a memory, for a traditional one in this line, you can hear 6 to 5 gigs. We have a latency. Latency is 1 to 2 milliseconds for a premium availability models. I explained that premium availability models, those are DTU premium and the vCore business critical. They're leveraging that. They have attached SSD to the nodes and keeping LDF and NDF files to the same SSDs. With the standard, everything else except the hyperscale is 5 to 10 milliseconds latency. They use the remote storage, basically, and they share that storage. They share it between the primary node, and there is no secondary node. There is just node with the spare capacity, which is gonna pull the data. Once that one is down, it's just gonna grab the data and relink to those NDF files. Now, I'm gonna show you 2 examples at the end of the session, which you're gonna see 2 different scenarios with the performance of hyperscale. That's the reason why I'm saying like the latency can vary, and that's exactly what it is. It depends on your usage pattern, on your workload. You need to understand your workload and say, okay, this is the architecture for me. This is deployment for me. So what you want to accomplish is getting your data from a cache. That's the first layer. It's your compute one. Then the second layer, the page server tier. So you want to read from a cache. And if you do, if your workload is sorry, this is like automatically switching the page. It's not me, but I'm gonna go back and as necessary. If you recognize your workload and say like, yes, that's for me, you're gonna have basically what you're getting from a premium availability model as business critical or premium service tier from DTU, 1 to 2 milliseconds latency. And I'm gonna show an example and test. So log throughput, this is really important, and you need to understand your log throughput because lots of customers I work with is struggling with this. They don't understand once you move to the traditional one and put 3 cores, you're not gonna get enough if you have a more throughput on your dedicated one at the moment. So the main reason for this, they need to guarantee you SLA they're offering you. So they need to sync if it's a business critical or if it's a DTU premium, that's fully sync commit kind of architecture. And it depends on vCores. What you see here, this is the max, 96 max per node, but that goes 96 above 8 cores. So below that, there is a mat in the back with the cores, you're getting the throughput. There is a resource page, Microsoft, you can see that. For a hyperscale, there is no ratio with the core. It's just 105 megabytes, regardless of number of cores. That's really important. And I'm going to explain you later. There is something called, this is the cap on the log throughput, but there is something called compute node throttling, but we're going to talk about it later, which is going to lower your, for a particular reason, is going to lower your throughput. So log size is up to 1 terabyte log size for a traditional one, unlimited log size for a hyperscale. Only limits you have in a single transaction needs to be finished in 1 terabyte size. Read scale out, one read scale out replica, and that's only for a premium DTU and business critical vCore. And for a hyperscale, you have 4 HA read scale out replicas and up to 30 name replicas. I'm not going to mention them here. I'm going to mention them in the next slides. And you have a geo replica as well. Backup and restore depending on the database size. Backups on a hyperscale are snapshot backups, and do not depend on the size. This is with the star. Why? I'm going to show you examples and speeds of restoring in the different region, the same region, same logical server, different storage type, and so on. It's going to be different results. So how does hyperscale works? How to accomplish that with what that architecture actually offering in the back and how that look like, how that works? We're going to talk about the premium compute node, secondary compute node. We're going to mention HA, that's read scale out and HA replicas, named replicas and geo replicas. We're going to talk about log service, page servers, really important, second tier, and Azure standard storage. So this is our compute nodes. On the compute nodes, we have a primary compute node and a secondary compute node. For a primary compute node, now since March, you can choose provision or you can choose the serverless. Once you deploy that, secondary is going to be exactly the same. Bear in mind that. Your HA, I'm talking about the HA, you can go up to 4, but you can create secondary name replica, secondary geo replica, which is by your desire. So for a primary one, when you're deploying, you have a 3 family now available. It's a standard series generation 5, which is, as we already mentioned, 80 cores and 625 gigs of memory. And you have a premium series and premium series memory optimized. The difference is in the core and the memory. First one is 128, and I believe is not sure. I think it's 625, same as the previous one. Actually, for a standard Gen 5 is 415 now, I believe. And premium series memory optimized is around 800 gigs, as we already mentioned in one of the slides up. For a serverless, you have just generation 5, 80 cores, and the memory is low. It's 240 max. And 0.5 up to 10 is the minimum of vCores you can go for a serverless. Obviously, you need to put some level from where it should start. So once you deploy all the traffic, read write, read only, depending if it's read only, is going to go to the secondary. If you put application intent read only, it's going to redirect you to the secondary. Otherwise, it's going to go to the primary. Primary has a resilient buffer pool extension, which is non-covering cache. It's SSD drive in the back. It has as well the buffer pool there. Non-covering cache, it's basically just those pages you actually using recently or used a lot is cached there. And if there is a request from application, it's going to be, if that page is not there, it's going to be added. We're going to show you, I'm going to explain how it's going to be added later on. For a secondaries, as you can see, those HA, named replica, and geo replica, you don't have those options on a traditional one. This is really important to understand. So named replica is one of great addition. It's not cheap, we can say, but it's a great addition. So for HA and the read scale out, you can go up to 4, same configuration as the primary, no dedicated connection string. You can't control them. You can't choose which one is going to take the role. Named replica is up to 30 named replica, desired compute tier, so you can put anything you want. Size, vCores number, and so on. And you have a dedicated connection string. It's read-only, obviously. But you can actually specify, like saying, okay, I have a team which is doing just analytics. I have a team which is doing developing. I have a team which is doing this and that, some kind of OLAP process or whatever. You can give them different nodes with async data there from directly from production. And you have a geo replica, which is for a DR scenario. So obviously, when you deploy, you need to deploy to different logical SQL server, different region, and you can change compute tier as well. So bear in mind that latency can be different on the different replicas. So if you have a multiple of them and you check the latency, can be different. But it's really fast. And as I said, it's a good thing we went to the log service, because here you can see the secondary replica on this side, page server on this side. This is the async communication with the log service. This is the fully sync communication with the primary compute. So in the previous examples, when we talk about traditional one, we say that if you have a DTU premium, or you have a vCore business critical, those are in full synced commit mode. So they need to talk with each other all the time. This is not how the hyperscale works. Hyperscale actually primary compute node do not communicate with the secondaries and the page service. Communicate with the log service, and the log service actually giving him information to the primary node. Where is the data, on which page server holding the data, and what needs to be updated on the secondary one. They all have a resilient buffer pool extension on SSDs. Size depends, as I already explained, on a primary and the secondary. It's on the compute node in general. It's a ratio with your number of cores and the memory. And if you have 2 cores, that's around 5 gigs per core. That's 10 gigs of memory, a little bit about that. Times 3, you have a 30 gigs of your resilient buffer pool extension for a caching, plus the buffer pool as well. And the page server is a bit different. This is a covering cache, but we're gonna explain that in one of the next slides. So what is important here? It's important understanding what are the layers, because the log service obviously have multiple layers of your log service here. You have a landing zone, you have a long-term storage here, and you have a Xlog processor, or what you can call it log service as well process here, which is holding the staging area, log broker with the SSD cache. What is the role here? So once you start writing the data to your database, what primary do, and the synced, primary fully synced, directly write that data send that data to the landing zone and send the data to the staging area. When that log block is hardened and it's done, staging area is not doing anything until get that information back. When it's confirmed, the staging area passed to the log broker. Log broker updates all those page servers and secondary HA replica if necessary with all those informations and syncing them. So this is now available because it's hardened in the landing zone. If it's available, it's gonna be sent to the long-term storage. This long-term storage we are using for a point-in-time recovery, and we're gonna see how that look like once we go to the Azure storage and show the process. I'm gonna show the process of point-in-time recovery. So this is how the log service works. It's a multi-tier, like even log service is multi-tier here. And it's really important to understand it's 105 gigs limit cap on a log. So about that is going to happen, that is going to be capped and start throttling. But there is another thing which is called throttling of the primary compute replica, which means that in one threshold, I think it's 1 gig, but I might be wrong. If there is a delay with this async updates on the page and secondaries, and there is a delay which is about the threshold, what Hyperscale is going to do is going to start throttling on the primary compute. And this 105 is not going to be 105, it's going to be less than that. Until it's picked up where it should be, all of those LSNs are up to date, then it's going to continue again. So this is the page server, which it's hard to say most important because everything here is really important, including the log service and compute and the storage, obviously. But the page server is actually which is giving you that scalability, horizontal scalability. So what you can do is once you add more data, he's gonna spin another page server in the back, and you add more data, fill that page file, is gonna spin another one, it's gonna spin another one, it's gonna spin another one, it's gonna go up to the size of 100 terabytes. And you don't need to control that. And this is what is actually giving you that restore and backup speed, because you have a snapshots, backup snapshots on a Azure storage. You have a snapshot, but those snapshots are like just subsets of all of those page server files, as you can see here. So why I have a different size here as a file size and the maximum file size. I on purpose did this example like this because the reason why you have 512 and 384 and then 128, 128, 128, this database was migrated from traditional one and was bigger than 1 terabyte. Was 1.2 or something, 1.3. Once I migrated that, your engine, hyperscale engine, decide I'm gonna split this 512, 512, 384. Like a year ago, that was completely different how it worked. They changed that now in this way. I'm not gonna go how it was before. I just want to point out that this is something which Microsoft tried to improve even more, because this is gonna give you that speed of backup and restore. So if you keep all those files in 128 kind of gigabyte size, it's much, because they all work in parallel when they're restoring, it's much easier to restore that database. In this case, your restore is going to take as long as your biggest file size is. So that's 512 in this case. But you can see after 512, 384, you can see that after that, when I was adding more data to the hyperscale database, every single one of those was going up to 128, 128, 128. And then as soon as you reach some threshold, like 90 gigs here, it's going to create a new one. And it's just going to add them, and so on. So every page server is just controlling the subsets of data of whatever size is, and RBPX resilient buffer pool extension cache is the covering cache, and they have a buffer pool as well there. It's stateless, so if it's gone, your data is still on Azure storage, it's still there. And this is how it's looked like. This is the kind of like maybe the big advantage of it, of hyperscale architecture. Each page server can contain between 128 gigs up to 1 terabyte. To be honest, I did like, I don't know, 1,000 tests. I never had more than 512. I'm not sure if I was unlucky, but they say like it can go up to 1 terabyte. Each page, what is important to understand here, you can see in the back, each page server actually has a replica. It's active configuration, and it's for a purpose, redundancy and high availability. We have Azure Storage. That's the last tier there. Azure Storage is Azure Standard Storage, nothing particular, usual standard storage. But you can see that page server communicate with Azure Standard Storage, and our log service have long-term storage, which is exactly Azure Standard Storage, the same one, but it's keeping those hardened log blocks for a purpose of point-in-time recovery. So before we go to the point-in-time recovery process, I just want to explain that Hyperscale utilize that storage and hold MDF and LDF, just to be clear, on the storage side. Everything else in between is the cached layers. So what we're going to get from that is the extremely fast snapshot backups, regardless of database size. I explain why that regardless of database size is not quite, because if you move the database from a different, from a general purpose, standard traditional architecture, DTU, actually that's a vCore, sorry, my bad, vCore. If it's a more than 1 terabyte, you might end up with a 512. So 512 and 128 is not going to be the same. It's going to take as much as your biggest file takes, because they're all going to work in a parallel. So what you have as well, those snapshot backups, they're not going to have any impact on your compute. And that's really important. And those snapshot backup files is not, in fact, a full backup. It's small differential copies, kind of from a base file with a stamp on. So how the point-in-time recovery actually works? It's basically when you want to restore your database, you have that hyperscale deployed and it's working fine, and you're having all those backups, all those working in place, and you want to deploy to the same logical server but a different database. For some reason, you want to go back for a day. So when you choose your date, you're gonna have, it's what it's gonna do is gonna pull the latest snapshot for each one of those page servers. Gonna pull those snapshots, and then gonna find the sequence, the LSN of the oldest transaction from the latest snapshot. This is going to be that, but that's he looking that into log term storage, which is belonging to the log service. This is all log service here. So this is going to be backup, restore this fast, then add from there, add point in time where you want to go. So it's going to create a new page server. Those page servers going to sync from a snapshots. You see here? But new log service is going to sync the landing zone. Landing zone, as you can, if you go back when I was talking about the compute, when it's reading something, is going from directly attached to the landing zone. So that landing zone is on premium storage, because you want to be the fastest one. It's going to pull new log service, is going to pull the data from landing zone, and once primary is online, it will pick those logs from landing zone. So there is where your primary is getting the data off, and it's sending the data in as well at the same time. I hope this is understandable. It's not that easy, but if you kind of like put kind of like multiple examples to your head, you're gonna kind of get how that actually works. This is the part when I always want, when they're promoting this hyperscale, Microsoft usually say the constant time. It is a constant time, but it just means it's a constant time for that particular size. So the different size, that constant time obviously is going to change, but they guarantee you it's going to be similar every time. It is not, but I'm going to show you here in this example. This is the database which I was working on. It's just 2-page server. Its size is 120 gigs. You can see here all the details, but important is just 120 gigs. I want a 2-page server because one of those page servers can handle 512. One of those page servers can handle 128. Your restore and time is going to be 512 gigs in that case. They all work in parallel. But what is your biggest file? That's your restore time. So here in this example, we have a restore operation with the same region, same logical SQL server. So backup storage redundancy type is really important in a hyperscale. So when you say I want to restore the database from locally redundant storage to locally redundant storage, size is 120 gigs, it's going to take you around 6 minutes. If you do, it's the same region, same logical SQL server, just different database. If you change the type of your storage redundancy and go to the geo, it's going to take you 20 minutes plus. Because what you're now doing, you are moving the biggest file across. If you go with the geo-redundant storage and you want to go to local redundant storage, again, what you're doing, you're moving biggest file across. It's going to take you 26 minutes. It's not exactly the same. But to be fair, my environment was a bit busy, so it depends on your environment. When you're doing those testing, they need to be exactly the same, which is kind of hard. I couldn't just run different, like create a whole lab for it. So I was like doing a bunch of tests at the same time. But if you're doing geo to geo, you have a geo. It's a same region, same logical SQL, different database. I'm not changing the redundancy on my storage. It's going to be 5 minutes. So you can see if you try to change that redundancy, don't be surprised if your restore takes time. The second way of doing it is the geo restore operation to the different region. That there is no way to do in the same kind of like option, because kind of same logical server, because it's going to be different region. Obviously, if it's geo restore, it needs to be somewhere else. And you can see in both cases, in geo to local redundant is going to take time, and it should, because you're moving that across again. And there is no way to speed up that because there is a network latency, other things which going to influence that. And if it's a peer region, if it's not peer region, if it's a peer region, it's going to be much faster. But so on, so on. This was not the peer region, so maybe I should put the example with the peer region, so just to show how that looked like. So the next one, how this all works together. So we're gonna kind of go with the explaining the data reads, data writes, log throughput cap, primary compute. We already talked about this, but we're gonna mention it again just for a clearer picture of this. So what we have here, our application is send request. It can be application intent read only. If it's application intent read only, if there is available secondary replica, it's gonna go to secondary replica. But for the sake of easier explanation, I'm gonna say it's a read write and it's going to the compute node. Once it's gonna compute node, if you read some data from compute node, first it's gonna check the resilient buffer pool extension, then gonna check the buffer pool from it. If it's data there, if it's not, what primary needs to know which page server hold that particular page or that particular log block. So actually it's a get page command. So I would say page and stick with the page. It's gonna be get page LSN request, and it's gonna be created get page LSN request. The log service is gonna tell which page server having that data, and it's gonna be count as a remote read. So this is the fastest, this is second fastest. So after that is sent to the right page server, if page server has that data, that page, it's gonna send directly to the primary. If doesn't have that page, then it's gonna be created get log block request. And that get log block request is gonna go to the log service, and log service needs to update that to if it's necessary for a secondary, because those secondary RBPX resilient buffer pool extension files, cache, it's holding the data which is actually requested from application. So it's not gonna hold. This is as I said, it's not covering cache. It's not gonna hold every data there. It's gonna hold what is necessary, and as well, the size is different depending on the vCore, on the memory, and so on, which we already explained. You can't keep all the pages there. But if there is a request, get log block request for log service, then apply that log, return the page to the primary replica. This waiting time is going to be counted as a page IO latch. If you write the data, so you write on primary directly do that in parallel to the landing zone and xlog process or log service, call whatever you want, which we have here staging area, which I unfortunately didn't put in this small picture. Staging area, log broker, and the log cache. That staging area is not going to do anything until get information from a log block that write is hardened. When that is done, this staging area passing to the log broker updating the page server and secondary if necessary. So that's how that actually works in the back. Then we have that log throughput cap. As we said, it's a 105. If you go about that, the all gonna throttle is gonna be kept. But besides that, as we mentioned, you have a primary compute log throttling rate. If this async, because this is all async between the log and the page server and the secondary, this is a fully sync between the compute node. If this async is in delay and to the one threshold, I don't want to say numbers. I'm not quite sure what is the size of threshold on top of my head. I would need to check on that. If go above that and that delays is about the threshold, is going to start throttling below 105 megs until this all catch up, and then it's going to go as what has before. So we have 1 minute. Okay, I'm going to be fast. I have 2 more slides. I hope that's okay. This is the HammerDB T-proxy workload. It's basically for testing purpose, I use the HammerDB tool. It's free open source tool. It's heavily in use. Lots of DBAs, data specialists are using for testing their data environment. This tproc is just transaction processing benchmark, and it's derived from a TPC, which is standard specification. I use this to run against general purpose Gen 5. This is the vCore deployment, 8 cores, and business critical generation 5, 8 cores. This is the vCore business critical, and the hyperscale generation 5, 8 cores. So it's the same number of cores, different. This is basically traditional one. This is the hyperscale one. So what we're going to use, I'm not going to explain too much how this works. It's basically you build the schema, you insert the data, and then run the test workload on that, on top of that. But what are the warehouses and virtual users and so on? You need to go in there and test it. I explain actually really detailed in my book, but yeah, we don't have time for that. So number of warehouses is 50. In this case, a virtual user we're using 32. So what we're gonna do, we're gonna have 8 minutes of duration time for a test and 2 minutes for ramp up time, so 10 minutes overall for each scenario here. So this test completed with the 32 virtual users achieve around 60K of new orders per minute and 140K of transaction per minute. And the peak was, although peak is just a peak at one point, it's not that important, but it's around 170 if I see my eyes already. It's late here. So this is for Gen 5. So if you compare that with the business critical, you can see that we had a 60K, we have a 130K now. We have a 140 for transactions, we have a 308. So it's around 300 there. And the peak obviously is going to be way higher. Let's compare all that with the hyperscale. The first scenario, so the cache is the schema build is done. The data is inserted in database. As soon as that happens, you're gonna have your data within your resilient buffer pool extension kept there. All those cache is gonna be filled with the data, with the pages. So if you run in that condition and say 8 minutes duration, 2 minutes ramp up, that ramp up time is basically to connections start being stable, and then we're gonna do the test. You give 2 minutes actually kind of like the connections be stable, and then doing the test. Test completed for a same amount of virtual users. It's 120K. It's quite close to the business critical, and it's around in this case is 285K of transaction per minute. Again, quite close to the business critical, and peak. It's a bit less, but that peak, it might be like a second or something. It's just the highest peak. Please understand this first scenario one, I had results which are better than the business critical, but I didn't want to be misleading, because when I did 10, 20 tests or 100 tests, whatever number, I took like a little bit below average for a hyperscale, because I had the different things happening on the server. Those tests are sometimes a bit slower, sometimes go a bit faster, but the better performance. But I just wanted to give you a kind of example below average, like it's almost exactly, or at least we can say close, and I can guarantee it's going to accomplish, if you understand your workload and the pattern of usage, is going to accomplish the same results as going with the business critical. Scenario 2 is after the schema was built, after the data was inserted, I emptied the cache. I emptied the RBPX, resilient buffer pool extension cache. I empty buffer pool cache and everything on a computer and a page and everywhere. So what when I run that after that, you can see that dropped significantly to the 100K for a new orders, and then you can see the transaction per minute and peak. After some time, this will pick up and be as in scenario 1. But I just wanted to share with you how the workload and the usage can actually define the performance for a hyperscale. Because obviously it's data and earlier files, they're stored on a remote storage. It's Azure storage, standard storage. But we want to utilize those cache layers, so the compute and the page server. So let's wrap it up with this. This is the last slide. Why hyperscale? So rapid constant time compute scale up, scale down. Scale down and scale up is really fast. You can see the point-in-time recovery, how it works. It's really fast. You have unlimited log size. You have 100 terabyte size. You have a transaction log throughput regardless of number of cores, which is 105, up to 4 HA secondaries, but 30. This is like a numerous read scale out scenarios. Exactly what is written here. This is one of the best benefits because you can create a 30 named replicas suitable for more complex read scale out scenarios. So you can have multiple teams running directly or writing the query or using the reporting as a reporting server or whatever is like scenario you can imagine. I think it's kind of feasible in hyperscale because you have so many external options to do with that. It's async, but it's fast. And the async is not delay. Like I'm not sure what is the delay in there, but it's really small. Fast backups and restore. I explain you that can defer, can be different depending on you changing your storage type, redundancy type. You're doing G restore in some different location, which obviously you need to move the database, so it has to be. It takes some time, but if you need same local SQL, exactly logical SQL server you're using for a store, for a source, for a destination, it's going to be fast as it can be. It's going to be 5 minutes, literally. And in that case, doesn't really matter if your database, if you create a native database, which you're having like 10 gigs or having a 10 terabytes, all those files are 128 gigs. So it doesn't matter what is the size of your database, it's still going to be the same restore time. So it's multi-tier cached storage architecture. What can I say? I love it. I tested. I really enjoy that, and I'm using a lot. So I think it's Microsoft investing in that is going to be future because you can see how much limitations you may have with the traditional one. On do you go for a 4 terabytes on Azure SQL PaaS? Although much more companies nowadays actually trying to going from a traditional database and having all those shared tables for a customer, going to the database per tenant per customer, because now they're gonna release, I think, beginning of next year, 2024 is gonna be fleet management tool released, so you can manage 1,000 databases really easily. And I can see that Microsoft going that direction, but still, this can't find like really. Kind of like I have quite a few companies which are asking, and it's interesting moving from a traditional one to a hyperscale for multiple reasons, especially this secondaries and solving your all up kind of environment at the same time, analytics environment at the same time. Thank you all for attention. It was a bit longer than I expected. This is my details. And please, if there is any questions, and if I can answer now, I will answer now. If not, I can help you later on, if I don't know, obviously.
Thank you very much, Zoran.
I hope it was understandable. It's maybe too much information.
Yeah, it's a lot of information, but I think it was clear. Very interesting stuff. I see a comment here. Oh, about the recording. Okay, I'll answer that later.
Ah, cool.
We'll publish the recording in the meetup page. I have a question. Assuming I have a 100 terabyte database and I have data files of 128 gigs, this means I'm gonna have 800 files and 800 page servers. Is that correct?
Yeah. Yes.
Okay.
That's correct.
Okay. And regarding the restore time. Yeah. Sorry.
And regarding the restore time, that's the best thing because your restore time is going to be the size of your biggest file because they're going to restore in parallel, all of them, all of those subsets with the snapshots. And I showed you like that point in time recovery. So all those snapshots for a 128 gigs, they're going to be separately restored. And then just those tweaked transactions after, which is hardened transactions after, is going to be restored. But your restore time is going to be your biggest file. That's 128.
But only it's actually the size of the used pages within the file, not the entire file.
Yeah,
right?
yeah.
Okay,
yeah. I'm just saying that's the max you can get because what you said, it's exactly true. But how the hyperscale is working, he's trying to fill those pages. So majority is going to be filled. Just those new ones is going to be like kind of empty. But if you go from a general purpose and move 1.5 tera, you're gonna see a different size so then in that case, your restore time is gonna be your biggest file. Not even if you have 1,000 others, is like 128 or whatever.
Cool.
So
Thanks.
that page server, like if you have 512, obviously that's the time of restore then.
Right.
But that's just in case if you that's the reason why it says, and they don't want to put that specifically nowhere, but they say like up to 1 tera. But in which cases up to 1 tera? Only I to be just kind of like a disclosure, I never end up running the native one going above the 128. That doesn't mean it's not possible. Maybe if some huge transaction is there,
Yeah,
it might gonna behave
could
like
be
that. Yeah, I don't know. I didn't end up testing that up to that level. But what I tested is like when I do the migration, I see those big files, and I never reach above 512, which doesn't mean it's not possible. It's just probably scenarios and what kind of like what you mentioned. It's not what is allocated; it's actually what is in use. I'm guessing it's gonna dictate that.
Okay. Any other questions? Anyone? I guess not. Well, thank you very much again, Zoran.
Yeah, thanks for giving me this opportunity to speak in front of your group.
We'll publish the recording on the Meetup page later on.
Yeah, sure. Excellent. Thanks a lot.
Thank you very much.
Thanks a lot.
Bye.
Thanks. Bye.